All right, good morning. So I would like your permission to participate in a conversation with you guys. I hate doing presentations where I'm the only one speaking. So if you could help me out during this presentation, I like to ask questions and to get people involved. I know we have people online, so I'll try and repeat back what you guys say, but I want to make this as much of an interaction as possible so that I keep my energy throughout this presentation. So the objective of this presentation is for you guys to come out of it understanding when SLA is a good fit and when SLS is a good fit, the advantages, the disadvantages, and where it kind of fits in your ecosystem when you're bringing a product to market or manufacturing something. Got it. It skipped my agenda slide, so I'll just get into it. So I always like to start things on a really high level and start thinking of 3D printing as a whole as a type of manufacturing process. To oversimplify things, there are three manufacturing processes when you want to bring something to life, right? So we've got subtractive. Who in the crowd wants to tell me the advantage and disadvantage of using that type of manufacturing technique? Advantage, tolerance, materials, mass production. Disadvantage, if you're making a small quantity of things, it's very expensive. And since it's subtractive, there is a good amount of waste material. If you move to formative and injection molding, advantages, disadvantages. Anybody? No takers, no problem. Advantage, lead time, right? It takes a while sometimes to get a mold made. If there's any change made to your design, sorry, you got to make a new mold. But the advantage, you've got all the different plastics out there that you can use to make your parts and mass production. You got a low cost per part. Now, when you go to additive, what are our advantages and disadvantages? First advantage is your ability to make highly customized parts, right? So whenever there's a change or an improvement that you need to make, you can make that change on the fly and have your parts really quickly. You've got a lot of materials, but you don't have all the materials that you can use for injection molding. So that could be an advantage as well as a disadvantage. But the real disadvantage has to do with mass production. You can use additive technology to mass produce parts if your production run is in the $10,000 unit count. But when you get in the tens of thousands, that's where it's simply not a good fit. Another oversimplification that I'm going to make is the different types of applications being used for additive. I like to bucket them into 4 segments. Segment number 1, concept models. The key term here is it's just fit and form. Does it fit right? Does it feel right? Second piece, functional prototyping, like actually testing this part out in the field. Does it work the way I intend it to work? Manufacturing tools, so anything that you need to help you through the manufacturing process, whether it's an object to hold something, an object to measure something, anything along those lines that'll help you through your manufacturing process. And then the final piece is end use production, right? Like, are you actually using the 3D printer to make a part that's going to go out on the field? Quick note, a lot of the OEMs today are using their 3D printers to use end-use parts for their printers. It's a simple example of a type of part that's being end use that's used in 3D printing. So today I'm here to really highlight Form Labs. And Form Labs have dipped their toe into 2 types of technology. I'm going to go over those 2 different types of technology. First type of technology that Form Labs is using is, ooh, that moves. I have to be careful. SLA. So to oversimplify SLA, you've got a vat of liquid resin. You've got an energy source that's being applied to that vat of liquid resin that's curing your geometry layer by layer from bottom to top. The vat is made of one material, so your support material is made out of that same cured resin. Since these are thermosets, the main application you're going to use SLA for is your concept modeling and your functional prototyping. It's very rare that we find applications that are a good fit for SLA for end use, and I'll elaborate a little bit further in this presentation as to why. The short, quick explanation is that these parts, their mechanical properties will change over time when they're subject to UV light. When your parts out in the field, they're being hit by UV light at all times, hence changing the mechanical properties. Where all the testing you did, now the mechanical properties are different, which means your part might fail. So again, best for concept models and functional prototypes, not great for tooling, can be used for tooling, but not great for tooling, not great for end use. Formlabs has two printers that fall into this category. Printer number one is the really large printer that you see in the middle of the screen. That's their Form 3L. The little brother to the Form 3L is the Form 3. Main difference between the two technologies, size. Simple as that. You'll also see that in order to use these technologies, there's post-processing that needs to be done. So I just explained the printing process, the curing of the resin that happens in the vat of the printer. Once they come off of the printer, there are two additional steps that need to be done to that part for you to use those parts. You need to wash that part with IPA to remove that thin layer of resin that's on the part, or else you completely ruin your part tolerance when it cures. And then the second part is curing it. So when you heat it up and hit it with UV light, that thermoset then takes on its final mechanical form, essentially. What you see on the right-hand side of the screen are the two solutions that you need in order to wash and cure the parts. Basically, an agitation with IPA and a convection oven that's got UV light, if I were to oversimplify the solutions. Now moving to SLS, it's a very similar concept. But instead of a vat of liquid resin, you've got a sandbox full of powder. So you've got powder that's being sintered by an energy source. In this case, a laser, which makes which is what comprises SLS. It's sintering powder layer by layer from bottom to top. One of the key attributes to this process is that with all other additive processes, the weakest, I guess, axis of the part is on the Z-axis because you're binding the part layer by layer. When you're sintering parts, you don't have that weak point on the Z-axis. Your part is actually fully isotropic, so it's got a little bit more strength. Where you typically see SLS being used, you'll see it being used for end-use production. Companies will typically be using this technology to prototype, do their functional testing, and then use the technology as a bridge before they actually go into production and getting their injection mold made. And in some cases, when the unit count is low enough, let's say an enclosure for a radio, and they only need to make 5,000 units a year, then they don't need to get a mold made. Every new version of that enclosure, they can do it on their SLS 3D printer. So the Formlabs Fuse 1 comes in two parts. The printer itself, which you see on the left, that's where the powder is being sintered. And on is the depowdering station. So this is where you are post-processing your parts and removing all the powder. The great thing about this technology is that that powder that you did not sinter gets to be reused and reclaimed for your next build. Formlabs has a pretty good refresh rate where 30% of your powder for your next build needs to be fresh, where 70% is reclaimed. So for the most part, you're able to build parts without any waste. At the end of this presentation, I'm going to walk you through calculating your part cost between a part in SLA and a part in SLS for you to understand that process. In short, when you're building a cost analysis in SLS, you have to account for the potential waste if you're not able to keep that 70 to 30% ratio. Before going there, I want to walk you through the material selection that these two technologies have, because at the end of the day, it's these materials that allow you to meet those 4 buckets of applications. You're going to use a very different material for your concept modeling than you are going to, than the material that you're going to use for, let's say, a load-bearing fixture. The material properties for those 2 applications differ, and the price for those materials differ as well. So let's break those down. For Formlabs, the material that you're going to use for your prototyping are their standard materials. So they have a grayscale, white, black, gray. They have a clear material, a draft material, and then a color base, where basically you take a recipe book of colors where you could make your brand colors if you needed to in your realistic looking prototype. This material is the most cost effective and what you'll be using for your standard prototype. All of the materials that Formlabs has created, they're thermosets. So they don't actually have an exact replica in the real world. They're like materials. So this is a really good graph that walks you through all of the different materials that are popular in the market and their tensile strength and the like materials that Formlabs has to replicate the material properties of those materials in the real world. So I'm going to walk you through those materials that are going to be used in engineering and manufacturing processes. The good news is they've done a good job of naming these materials where the name describes what they actually are. That's, I think, a challenge in the market with thermosets. A lot of the thermoset materials that are out there have a numeration or a number where you're not exactly sure what it's going to be a good fit for. So high temp is a really good material for high temp applications, right? Pretty self-explanatory, with a heat deflection temperature of 238 degrees. So this is going to be a great material for functional prototyping as well as tooling applications that require a high heat deflection temperature. The next family of materials are their tough and durable materials. These are the most popular materials for manufacturing applications. So I'll walk you through their like materials in the market. I'll start with Tough 2000. The most commonly used material for basic prototyping and functional prototyping in the market today is ABS. So Tough 2000 mimics ABS's material properties. So a lot of companies are using Tough 2000 as their functional prototyping material. From there, the next material in the tough and durable family is Tough 1500. This is like nylon 11 in the real world. So really good for prosthetic applications, for example. So stiff and pliable material. And I have a really good visual for you in my next slide. Their final material in this family is durable. And this is really popular for consumer goods because most consumer goods are made out of polypropylene. So this is your polypropylene-like material. So it has a lot more flex. So let's say if you're making a Febreze deodorizer enclosure for your bathroom and you want to prototype that enclosure using Formlabs, durable material would most likely be the material that we use because it flexes like polypropylene. Here are two quick visual examples that show you the flex of TUF 1500 and durable material. Any questions so far? Cool, I will continue. Next family of materials are the rigid materials. So this is kind of like your glass-filled nylon. So they have two categories. One is more robust than the other. Your rigid 10K material will be really good for low volume injection molding. So for any of you that have used Stratasys PolyJet technology, this is very similar to their digital ABS, except for it's a little bit more robust, where your injection mold prototype, instead of lasting around 10 to 15 shots, you might get 100 shots out of that prototype. Your rigid 4K would be ideal for load-bearing fixtures or any type of manufacturing tool. So these two materials are really good for, again, functional prototyping, potentially end-use parts, but mainly it's for manufacturing tools. The next category of materials are your flexible materials. And this is a really good graph that describes how flexibility is measured in the market. It's measured in a Shore A and a Shore D. So the lower the number, the more flexible. So your Shore A5 is like a mouse pad. Shore A25 is kind of like a rubber band. Around 50 is an eraser, 65 is a tire, and 85 is like the wheel of your skateboard. Formlabs has two flexible materials in their portfolio. A Shore 80, which is their flexible material, which is more stiff, and elastic, which is the best way to describe it, very elastic. And I have two really good visuals to describe that. What I like that Formlabs did is that they made their material names really self-explanatory, where you know right away what material you're going to want to use for your application. The main consideration that you need to have with flexible materials is that the larger the part, especially on the Z, the more challenging it is going to be to print that part because of gravity, right? Since it's a flexible material and it's printing upside down, gravity is pulling down that part when it's going up and down into the bath of resin. So when printing a very large part out of one of these two flexible materials, typically elastic 50 is going to be very challenging just because of its flexibility and gravity. So typically the larger the part, the more likely that flexible 80 is going to be the better fit. Here's a good visual that describes the material property that flexible 80 has versus elastic 50. Essentially, elastic 50 jumps back into place significantly faster than flexible 80. It's much more stiff, flexible 80. So that summarizes Formlabs' resin portfolio for manufacturing. They have altogether over 30 different resins. I'm not going to go over all of them. Their other resins include materials that are a really good fit for medical applications. So they have ISO certifications that make them good with skin contact and other medical requirements that the medical industry will have. Now when you move to SLS, currently Formlabs has 3 different types of nylon powders that are available in the market. The first powder that I'm going to highlight is nylon 12. Their PA12 powder is, the best way to describe it, it's going to be your multi-use material. You can use it for prototyping, you can use it for tools. It's the best Swiss knife material there is for powder bed fusion. When you move to nylon 11 is going to be much better for your thin wall applications. So a lot of companies that are making enclosures that have very thin walls that, I don't know, enclosures that need to be attached to small animals in the wildlife. Nylon 11 is probably going to be a good material for that type of really small, thin-walled enclosure. And then your nylon 12 glass reinforced material is just going to be a more thermally stable material that is more stiff. So that might be a really good fit for a tooling application in your manufacturing process. So I want to pause there and slow down and let you guys ask some questions on materials. No takers. Oh, there we go. Thank you, sir. Great question. So dimensional accuracy is always a hard question to answer because it will vary depending on the geometry of the part and the material that you're using. The advertised part dimensional accuracy is plus or minus 0.2 millimeter or 7 thou, but you can do significantly better than that. That's more of the blanket statement that they're going to use because, again, it varies depending on the geometry you have and the material that you're using. You can do a lot better, is my short answer. Any other questions? So to add to that, I would say that your prototyping materials are going to have a tighter tolerance than your engineering materials. So on the resin side, your standard materials have by far the tightest tolerance. And on the powder side, your PA12 is going to have the tightest tolerance.
What's the size range of the powder?
Size range in what sense? I'm not sure off the top of my head. The way that I would describe the parts is that they have a grainy feel to them. They're not perfectly smooth to touch like a resin 3D printed part. Your resin parts outside of the areas that have touch points where support material is allocated, they are injection mold quality in terms of their surface finish. The key characteristics an individual describes when consulting with us on what solution to use. If they say, I've got really fine feature details and I'm showing these parts to people that don't understand additive technology, typically resin is going to be a really good fit for that description of what they're looking for because the part looks exactly like it was injection molded. If they say, I need something that's functional, I need a large quantity of parts, I need to be running production, or I've got 30 engineers that are all prototyping, that's typically when we'll probably start the conversation in SLS or multiple SLA printers. But to come back to your question, it's much more of a sandy, grainy feel. And I have parts by my booth that I'll be able to show you the difference side by side. Any other questions?
In the SLS powder bed, for multiple parts, does the software, does your slicer software automatically say like, all right, I need 25 parts? Or is it automatically placed in the build chamber?
Great question. So the question was around preparation for 3D printing for SLS. So I'm pretty sure Formlabs is using an Autodesk driver to pack parts in the build chamber. You have three options. Option one, you can pack it yourself based on you understanding the best orientation for your part for that process. In short, with both resin and powder-based systems, you want to be curing or sintering the smallest surface area possible because of the heat that's being applied. So that's the first consideration. So you can do it yourself. You can use their auto pack feature, which will pack the parts in any orientation or locked in an orientation that you choose. Or you can use third-party packing software that will do all of that thinking for you using an algorithm. And we typically recommend using third-party software when you're really using the technology for production. So for example, if you're running a service bureau, the value of using that third-party software in terms of time saving and part optimization is as clear as glass. When it's one company that's got a couple of engineers that are using it for functional prototyping, they can use the packing feature that Formlabs created and have a fantastic experience.
For identically shaped parts, SLA versus the SLS time.
Great question. So the question is around which technology is faster. So when we compare batch productions, SLS is the fastest technology out of every single printing technology that we represent. We have technology in each, in extrusion, resin, and powder. You can do the most units in a short period of time for powder. If you were to only print one part, all three technologies are pretty comparable. I wouldn't say that one is astronomically faster than the other. Most companies print overnight when they're printing one part, and for the most part, that part is available the next day. I will say though that it depends on the print settings. With resin-based printers, some companies are using it for jewelry applications, which have the most minuscule fine feature details, which is why the technology can go down to a quarter of a millimeter in layer height, so 25 microns. Those parts take a significant amount of time, right? Like if you were to print on the Form 3L, this printer that's like 13 by 9 by 12, at 25 microns, full build envelope, I wouldn't be surprised if that part takes 2 weeks to complete at that layer height. But for the most part, my short answer is one part, all of them are comparable. When you start printing large quantity of parts, that's where SLS is the winner, hands down. Any other questions? So I have a really good example to walk you through in that vein of comparing the two technologies side by side in terms of time and cost per unit. So I've got an example of a component, a basic circular component that a company might want to make. This component, one single unit at 100 microns in SLA will take approximately 5 hours. And the part cost calculation for resin is really straightforward. It's milliliters used for the actual part, and it's a solid part, it's not sparse, plus the support material, so the total volume in milliliters used multiplied by your cost per milliliter. So in this case, the part, including its support material, is 44 1/3 milliliters that it's going to use. One cartridge of resin is $149 in that material, so your part cost is $6.61. Whether you print one part or 30 parts in that one build, your part cost stays consistent. When you move to SLS, since you're reclaiming powder and you can only use 70% reclaimed powder and 30% fresh, the density of the build needs to get close to that 30% mark. Or there will come a time where you've got too much reclaimed powder that you can't use in your next build. Does that make sense? So looking at this exact part, you're using 0.04 kilograms of powder, but your density of build across that build envelope is only 12%. So if I were to print this same part over and over again, the way that it is now, I have 18% of that build that I will eventually not be able to reclaim. So companies, when they're calculating their part cost, if it's below that 30% mark, will account for that powder that can't be reclaimed that they're going to have to throw away. What does that calculation look like? The true part cost is $4, which is material used times your cost per kilo. When you account for the powder that you could throw away, that's 17% of that powder, that makes the part cost jump up to $11. So the range on a one-off is $4 to $11 if everything stayed constant. But most companies, when they're using this technology, they're not printing one part, they're printing a batch of parts. They're either printing several different iterations at once, or they're using it for production. What would that look like on a production standpoint on the Fuse 1? So you would print, sorry, I need to look at my notes because I thought off the top of my head. It would take 58 hours to print 98 parts, thank you. So instead of a 5-hour one part, you've got 98 parts, 100 parts in pretty much 3 days. So that's a really good live example of the contrast of volume that you can do between the two technologies. And the post-processing is going to be very different on removing breakaway support material on 98 parts using resin 3D printers versus dusting off powder from an SLS 3D. Since the pack density here is 58%, so above that 30% mark, each part is going to be its true material cost of 4 bucks. So to summarize, when you're doing one-offs, your part cost can range, in SLA, it's going to be constant, right? Whether you make one or many. With SLS, whether you make one or many is going to determine the range of your part cost. To summarize the two technologies, when SLA is going to be a good fit is when you're going to be using some of these keywords. Number one, I'm just prototyping. I'm using this technology for concept models to check fit and form, to do early phase iterations of my geometry to validate that what I'm thinking is correct. I want to test its functionality and not go any further. I don't necessarily want this product to go out on the field. I'm looking for the smoothest surface finish possible. I want injection mold quality parts. And I'm looking for fine feature details. Those are all the key words that you will be describing you're looking for where SLA is going to be a good fit. With SLS, you can have a lot of those same terms, but what you add to that is a fully isotropic part that can be used for end use. So you can use it as a batch, like you can use the technology for batch production. You don't have support material, so it's a much easier technology to use in terms of post-processing. You're typically looking for a larger quantity of parts. Any questions? Super. I'd love to invite you to come by my booth, take a look at the different parts and the quality of parts between the two different technologies. And if you have components that you would like to print on any of these technologies in any of these materials to see how they will react in your application, please come by my booth and set that up.
So I'm interested in getting started in plastic printing. I have basically multiple choices, building printer, resin, whatever. What's the thought process that I should go through to determine which is best for my application? Well, let's just say I'm a machine shop looking maybe to do prototyping and fixing it.
Sure. So the question is how to figure out what type of printer to use for my machine shop. So that's the golden question, right? It's like, what car am I going to buy for everyday driving? And there's really no perfect answer. That is a blanket statement. It's really dependent on the application and what you're looking for. But if I were to oversimplify my discovery, I want to find out, first of all, which of those 4 buckets they fall into. Do they want to use it for concept models? Do they want to use it for prototyping, like functional prototyping? Do they want to use it for tools? And then do they want to use it for end-use production? So let's summarize those different technologies for those 4 applications. Resin, the best for concept model, right? Like you can make a part that looks that has injection mold quality, the most realistic. Someone that's never seen a 3D printed part won't think that it's 3D printed. When you go into functional prototyping, I would say that extrusion and SLS are a better fit for functional prototyping than SLA. I typically start the conversation with extrusion because the barrier to entry for extrusion is significantly lower than powder bed, and it's easy to implement, right? Like you can take the parts right off the printer and they can be used. When you want to use it for manufacturing tools, same thing, FDM, so extrusion and SLS are the best fit. But same thing, I typically start the conversation with extrusion because the barrier to entry is lower. And for manufacturing tools, there's the widest range of materials for extrusion. So tooling applications have a variety of chemical requirements that typically FDM is a really good fit for those types of applications. And then for the final bucket, batch production, I start the conversation with SLS because it's the best price to performance for that type of application. So long answer, but I think you get my drift.
And maybe talk about what's post-processing involved with SLS.
Sure. So post-processing with SLS is depowdering the parts. So when the print job is done, you've got basically a sandbox full of powder that contains both the sintered parts and the powder that hasn't been sintered. That powder that hasn't been sintered acts as a support material, but also needs to be reclaimed. So let's go back to the fuse one. So that reclaiming process happens in this solution, where you're basically reclaiming all that powder to go into your next build. After that, your part still technically has a small coat of powder on top of it, and there are a variety of different post-processing techniques you can use to remove that powder. You can manually remove it with glass media, manually. You can get a really inexpensive tumbler, like a Harbor Freight that is used in the jewelry industry, to tumble the parts. Or if you're using a batch production and you don't want it to be manual, companies like AMT and Dimension create automated post-processing equipment to media blast and tumble the parts automatically. So the question was, with plastic powder, do you have the explosion risk like you do with metal powder? The explosion risk is with the vacuum, which is why you can't just use a shop vac to clean your space. You actually have to use a class 2 explosion-proof vacuum. Outside of that, it's safe. It's not like metal where they're reactive and you need a special room, grounded pads, and Tyvek clothing when you're working with that type of equipment, depending on which type of metal equipment it is, right? There's some metal technology that can sit in your office. We have metal printers that are in a safe desk space, if that makes sense. But short answer, not at all the same level of considerations that you need to have for SLS powder technology as you do for metal powder. in the same vein, when it comes to facility requirements, your main consideration is that your SLA printers, any resin printer cannot be in the same room as a powder printers. They need to be in separate rooms. The powder will contaminate the resin printers. Your resin printers can live with other printers, like extrusion-based printers, but they cannot live with the powder. Any last questions? Mm-hmm. Sure. So two-part answer. So first part is around so adoption rate and what industries are using it. So let's start with adoption rate. So I would say that in the past 5 years, companies have accelerated their adoption to 3D printing because more and more engineers have 3D printers at home. So I would say from 2015 to 2020, more individuals got Prusas, Enders, Pulses, basically printers that come from the RepRap movement where the patents expired in the late 2008, 2009s. Engineers now have their printers at home and are pushing their companies to adopt the technology because a lot of the parts that they are running for the printer, for their company, they're doing with their printer at home and are pushing them to adopt the printer for business use. So I would say more and more companies are going from just that hobbyist type of printer to a solution that can hit tolerance consistently, that can do more materials, that has a more robust experience. Furthermore, I would say that the pandemic accelerated the adoption of 3D printing like no other. I don't know a single OEM, unless the technology didn't have a strong value proposition, that didn't have their best year last year. Same with the distributor, because companies needed to find ways to overcome supply chain disruption, continue to innovate, give their engineers tools to work from home on engineering projects. So we saw more companies adopt the technology last year than ever before. Furthermore, metal, we had a record year in metal. And if you look at industry projections, they're projecting this decade, 2020 to 2030, for adoption of metal 3D printing to go from 23% to 38%. So that's almost double the adoption in this decade because metal is becoming affordable. I would say, yeah, that would probably be the main thing, is that companies like Desktop Metal, Markforged, Exact Metal are making solutions that are under $1 million. So that's a much easier requisition that you can make in terms of ROI to adopt the technology. Now, second part of your question is around industries that are using the technology, and I'll echo my colleague from the first presentation that this technology is being used across all industries, right? It's being used by educators in K-12 or higher ed for research. It's being used by artists, whether it's in the entertainment industry, like, I don't know, like Cirque du Soleil or that type of entertainment, to Hollywood. It's being used by all sorts of manufacturers. Any company that's making a product will probably want to prototype that idea and validate their design. Furthermore, they could use it through the manufacturing process. So yeah, I echo Andrew's comment that this technology is a Swiss knife. It's being used by everyone. It's being used by my kid at home today. So a little bit of everything. Cool. Thank you very much.